Hello everyone and welcome to our C1 Atomic Structure Review lesson. I'm Mrs Jennison and I'm an Associate Director for Outward Grange Academies Trust. Our topic question for C1 is how are elements arranged and what determines their properties? We're going to start this topic by looking at the history of the atom and atomic structure. Over time, scientists have had different understandings of what an atom is, and it's important that we know some of the scientists who contributed to our understanding of an atom. We're going to start with Democritus, and Democritus believed that nothing exists except from atoms and empty space, and everything else is opinion. Now, what he said is he believed that substances could be divided many times until we achieved the smallest piece, and the smallest piece would be an atom. He also suggested that these atoms may have different shapes and sizes. Now, at the time, his theory was not widely acknowledged, and it actually took a very long time for it to be developed any further due to contradictory ideas. So in 1803, John Dalton proposed his theory of the atom, and he essentially agreed with Democritus, but he did say that he thinks that the atoms would be like spheres, and again, they would all be different masses and sizes. Now, he added a little bit to this, and he said that all atoms of the same element would be identical, and that atoms can't be created or destroyed but rearranged, and that atoms could combine and form compounds. So he did add a little bit more to that previous theory. So J.J. Thomson in 1897 discovered electrons, and he thought if an atom is spherical, the electrons must be embedded in the atom, and because the electrons he found were negative, the rest of the atom must be positive. A little bit like this small diagram here, although I'll put an enlarged version at the end of this section. And he said it would be like the plums in a pudding. So essentially a little bit like these currants in this Christmas pudding, they would be the electrons in this case, and they are embedded throughout the atom. So here's a larger diagram for you to see that. Negative electrons embedded in a ball of positive charge. Now, a few years later, Ernest Rutherford made a further discovery about atomic structure. He performed an experiment that proved that an atom is not like a plum pudding at all. So he found that the centre of an atom was where the mass was mainly concentrated, and that was a dense section of positive charged, and he called that the nucleus. He found also that the rest of the atom was essentially empty space surrounded by the electrons. So the electrons were orbiting this dense positive nucleus. And he found this through experimentation. This is a model which can be used to demonstrate Rutherford's alpha particle scattering experiment. The hoops and balloons behind me represent his sheet of gold, where the balloons are the positive nuclei. Now, Rutherford expected his experiment to actually prove the plum pudding model. He thought that his positive alpha particles, which will come out of this, would pass straight through the amorphous blob of positive charge, which had the electrons embedded in it. However, he found that around 1 in 8,000 of his alpha particles actually bounced back because it hit the positive nucleus. So this led Rutherford to two conclusions. The first one was that the majority of an atom is actually empty space, and that was represented by the alpha particles passing through the empty space. However, there is also a part of the atom that is where most of the mass is concentrated, and this part of the atom is positively charged and is the nucleus. And that is why some of his alpha particles
bounced back.
So further to that experiment, Niels Bohr in 1913 actually performed some further experimentation, and he discovered that the electrons actually orbit the nucleus in different energy levels, and they sometimes are referred to as shells. And he found that there was more than one, and that the electron shells had different energy levels. And that now becomes quite similar to what we know in terms of electron configuration. So in Bohr's configuration, he has 2 electrons in the inner shell and up to 8 in the following shells, with that positive nucleus with the protons in the centre of the atom. But there's still no neutrons, and it's because the neutrons took a little bit more time to discover. And so our final piece of work is to look at James Chadwick, and in 1932 James Chadwick discovered the neutron, and he did that in doing experiments with isotopes, and the discovery of the neutron obviously helped him in explaining what an isotope was. So first we had Democritus and his atoms, then Dalton with atoms, and every element only has one type of atom. They're all different shapes and sizes. Then we had Thomson, who discovered electrons and proposed the plum pudding model. Then Rutherford discovered the positive nucleus and proposed the nuclear model. Bohr discovered the electron configuration in orbitals of different energy levels. And then Chadwick, who discovered neutrons. The majority of these developments did occur due to improvements in technology, and there has been further development since Chadwick's work, but now it's time for us to look at what we need to know for our GCSE. And the first thing is that atoms are very small. They have a radius of about 0.1 nanometers, and the radius of the nucleus is less than 1/10,000th that of the atom, which implies that the majority of an atom is actually empty space. Now you should know that we have a nucleus in the centre, and this consists of neutrons and protons, and surrounding that nucleus we have electrons in their shells. Now we need to make sure that we know the relative charges and the relative masses of each of these subatomic particles, and that's what we refer to protons, neutrons and electrons. The protons have a relative charge of +1 and a relative mass of 1, and their location is in the nucleus. Electrons have a relative charge of -1, but their mass is very small, so that doesn't contribute to the atomic mass number. The location of electrons is in the shells, orbiting that positive nucleus. Then finally we have the neutrons, which have a relative charge of 0, but they also have a relative mass of 1, and their location is in the nucleus. So to find out how many of each of these subatomic particles are, we use the periodic table, and for every element on the periodic table there are 2 numbers. There is the atomic number, which is the number of protons in the atom, and there is the mass number, which is the total number of protons and neutrons in the atom. Okay, it's essentially the mass of the nucleus, and we can use that to work out the numbers of each of those subatomic particles, as long as we remember that an atom has no overall charge. So the number of protons, which are positive, will be equal to the number of electrons. So let's have a work through some of these. So if we look at chromium, we've got 2 numbers. The first one is the atomic number, which in this case is 24. That tells us that chromium has 24 protons, and because an atom has no overall charge, there must also be 24 electrons. To work out the number of neutrons, we use the mass number. So the number of neutrons will be the mass, 52, take away the number of protons, which is 24, which leaves chromium with 28 neutrons. Let's do another one. So argon has an atomic number of 18, so it has 18 positive protons, so there must also be 18 negative electrons. To work out our neutrons, it is our mass number, 40, take away the number of protons, which leaves us with 22 neutrons. So now we need to look at how the electrons are arranged in an atom. Electron shells fill in a particular way. In this small model, I'll be using blue liquid as my electrons. Now, electrons will always fill the lowest energy level first. Until that energy level is completely filled, it will not yet start to fill the second energy level. Just in the same way that the second beaker wasn't filled until the first small lowest energy level was filled. Now that continues throughout the entire shells of the atom. They will not fill their next shell until the one before is completed. And again, as you look, as those levels continue to rise, they are getting more and more electrons. So electrons fill from the first lowest energy shell, which was our first small beaker. Once that one's filled, it'll fill the next energy level. And once the second energy level is filled, it will start to fill the third. So remember that each shell has a maximum number of electrons it can hold, and it fills the first energy level first. So the first shell will hold a maximum of 2 electrons, the second shell holds a maximum of 8 electrons, and then so on. So if we look at argon, argon has 18 electrons. So to arrange those, there would be 2 in the first shell, 8 in the second shell, and then 8 in the final shell. And you can see that in the shells that are drawn and in the configuration written at the bottom of that diagram. If we look at phosphorus, phosphorus has 15 electrons. So there will be 2 in the first shell, 8 in the second shell, and then 5 in the final shell. One more, if we look at sodium, sodium's got 11 electrons. So they would be arranged 2, then 8, then 1. Now it's time for us to look at isotopes. Now on the screen there are 2 isotopes of carbon. The easiest way to discover what an isotope is to work out how many subatomic particles each of these carbons has. The first carbon, carbon 12, has 6 protons, 6 electrons, and 6 neutrons. Carbon 13 has 6 protons, 6 electrons, but this time it has 7 neutrons. Isotopes have the same number of protons and electrons, but they differ in their number of neutrons, and that is why the mass number is different. Now it's worth adding here that the atomic mass you see on the periodic table is actually an average value, and that takes into account the abundance of the different isotopes of that element. So now we've looked at atomic structure, we can start to look at the periodic table and its development. Now the early scientists wanted to find order to the elements, but they had limited information, as a lot of that work was carried out prior to us knowing about the subatomic particles. Also, some elements had not been discovered. So let's have a look at some of their work. The first scientist we're going to briefly look at is bromine, and he organised the elements into triads, which is groups of 3. And those groups of 3 had similar chemical properties. So they would all react in similar ways with oxygen, with acids. They had similar properties, and he called them his triads. We also have Newland, who arranged the elements in order of their atomic weights, which was the information he had at the time, from lowest to highest, but he organised them in rows of 8, which is what he called his octaves. Now, he did initially have quite a lot of the groups, the columns, match in terms of their chemical properties. However, it did start to go wrong at times where he had to put 2 elements in the same box, for example, or where he ended up with metals and non-metals in the same columns. So there were some issues with his law of octaves. So in 1869, Mendeleev organised the elements in order of increasing atomic weight again, but this time he ensured that the groups had similar chemical properties. And to make sure that that occurred, at times he left gaps for undiscovered elements, so that he would always have elements with similar chemical properties in the same groups. Now, if you look at Mendeleev's periodic table matched up to Dobrina's triads, you can see that the triads did end up in the same column. So he did have some crossover between those two early periodic tables. And the little squares with the white hatching, they were Dobrina's triads, if you can't quite see that on your screen. So to summarise these, we have Dobrina, which organised the elements into groups of 3 called triads. They had similar properties. Newlands, which ordered them in order of increasing atomic weight in rows of 7. And Mendeleev, with ordering increasing weight. And he also ensured that the groups had similar properties and left gaps for unknown elements. Now, Mendeleev was actually the closest, and he didn't simply leave it at his periodic table. What he also did is he predicted the properties of some of the undiscovered elements. The issue was that his work wasn't really recognised, as he couldn't explain the presence of those gaps, and simply stating that they were unknown wasn't sufficient to justify them. He also wasn't as respected as other chemists, so that did cause some issues with his work being acknowledged. Once those elements were discovered, Mendeleev's properties were incredibly similar, and 3 of the elements, gallium, scandium and germanium, were found within 20 years of Mendeleev predicting their properties. So we're going to have a look at a couple of these. So if we look at gallium first, when Mendeleev predicted their properties, he called it Eka aluminum because it was next to aluminium in his periodic table. And as you can see, the atomic mass is very close to what the atomic mass of gallium was. The density was very close, which he predicted. And he also predicted a low melting point, and 29.76 is an incredibly low melting point for a metal. Similar with Eka silicon, which was discovered and named germanium. The atomic mass he predicted was very close, as was the density, and he also predicted a high melting point. Following the work of Mendeleev and the discovery of many other elements, including the entirety of group 0, we have arrived at the modern periodic table. The periodic table now also links to atomic structure, specifically electron configuration.
Hi everyone, this is the periodic table of elements, and this is the particular one that you would receive in an exam. Now what I'm going to do in this video is I'm just going to annotate this with some really key features that would help you in using it. So the first key feature is the key in the middle. Now the key tells us what every single number and symbol represents on this table. Now in that you can see that we've got the atomic proton number, which is the bottom number on each element, and it is the lower number. Then we've got the atomic mass. Now the proton number is the number of protons, and the relative atomic mass is the mass of the nucleus, so it is the number of protons added to the number of neutrons. If we look at the periodic table, we can see that there are some patterns to its arrangement. So the first thing is that it is arranged in order of increasing atomic number, which means every time we go across, the element gains one proton. So arranged, this is the first way it's arranged, increasing atomic number. The second way it is arranged is to do with the groups. Now the groups are the columns in the periodic table. And what the groups represent is the number of electrons in the outer shell of that element. So every element in group 1 will have 1 electron in its outer shell. Every element in group 4 will have 4 electrons in its outer shell. The next thing we need to know about is the periods. Now the periods represents the number of shells that each element has. So if we looked at helium, helium's got 2 electrons and only 1 shell because it's in the first period. Neon has got 10 electrons, 2 in the first shell, and then 8 in the second shell because it's in the second period. Argon has got 18 electrons, 2, then 8, then another 8. So dependent on an element's location in that periodic table, we can find out pretty quickly how many electrons that element has and how they are arranged. So if I just pick one at random now, beryllium. Beryllium is 2 rows down, so there are 2 shells, and it's in group 2. So the second shell will have 2 electrons. So beryllium would have 2 electrons, then another 2. Now, there are a few other things we need to know when we are using our periodic table. And the first thing is a quick way to figure out where our metals and our non-metals are. So if we find aluminium and we draw like a staircase going around aluminium all the way down to the bottom of that periodic table, typically anything on the left of that would be metal, and anything on the right of that would be a non-metal. There are just a couple of specific groups that we need to know about now. So group 1 is our alkali metals. Group 2 is the alkali earth metals. This middle block is the transition metals. Group 7 is the halogens. And group 0 is the noble gases. Remember that group 0 is unreactive because it has a full outer electron shell. So there we go. That's our annotated periodic table.
So as seen in the video, the periodic table is in order of increasing atomic number, and there are groups, which are the columns, and there are periods, which are the rows. The group tells us the number of electrons in the outer shell, and the period tells us how many shells. And don't forget, hydrogen and helium are the first shell. Now we need to look at some groups in a little bit more detail. So first we're going to start with group 0, which is the noble gases. Now the noble gases are so unreactive that they were very difficult to identify. The first noble gas, helium, was discovered on the Sun in 1868 by Ramsay and Travers. It was actually not known to exist on Earth until 1895. So that suggests how unreactive these gases actually are. And they're unreactive because of the full outer shell. So if you draw the electron configuration of all of the elements in group 0, I've just put the first 3 on the slide to show you, they all have a full outer shell. As you go down the group, the atomic radius increases because you are adding another electron shell, which means the atoms get bigger. And because of that, the boiling points also increase. Our next group to look at is group 1, also known as the alkali metals. Now, all alkali metals react with oxygen in the air, and when they do that, they form metal oxides, and that produces a layer of dull oxide on the surface of the metal called tarnish, as seen in the diagram on the right. The alkali metals are often stored in oil because of this. The oil prevents them from reacting with the oxygen and tarnishing. Now I've drawn the first 3 elements of group 1, lithium, sodium and potassium, and as you can see, they all have 1 electron in their outer shell. And because of that, they will all react in similar ways with oxygen, water and chlorine. When they react with water, they produce alkali solutions. And as you go down the group, the atomic radius increases, the reactivity of these metals increases, but the melting and boiling points of these metals decrease.
This is Jenison here, and today I'm going to be showing you the reaction of group 1 metals with water. So for this investigation, I'm going to need samples of group 1 metals. So I've got lithium, sodium and potassium, and you'll see a little bit better in a bit. All of these metals are stored in oil because they are so reactive with the air and the water vapour in the air. I've got a scalpel and some tweezers in which to cut those samples and a white towel to do it on with some filter paper. That's there to actually absorb the oil. And then I've got a water trough and I've got 2 very small beakers and some universal indicator, and that's to test the water before and after the investigation. Now, if I was doing this in my classroom with all of my students, I would have a safety screen over this experiment to protect them from any harm. However, because it's just me and the camera today, I'm not going to use that so you can see the experiment a little bit better. However, in terms of safety, I have got my safety goggles on and my lab coat, and I'm also going to tie my hair up before we do this because some of these metals cause exothermic reactions, and that causes them to be flammable. So first of all, we are going to look at the investigation of lithium and water. So I'm going to take a piece of lithium out of the jar containing oil and place it onto the filter paper, like I said, to dry off and remove some of that oil from the surface. You may see at the moment that the lithium is quite dull on the edges, and that's actually because it's reacted. So what I'm going to do is I'm going to cut it to make sure that I've got a shiny edge. I'm not sure how well you can see that on the camera, but you should see that it's a little bit shinier now.
And if I've got that, then that will have a much better reaction. Place the lithium into this water. I'm just going to take a small sample using a small beaker for me to test with the universal indicator. I'm going to test that at the end alongside a small sample of the water that is after the investigations. Now that I've done that, I'm going to place using tongs a small piece of lithium into that water. I'm just going to use this to get it off the tongs because it's stuck on. Now remember, you should be recording your observations, so keep an eye on the lithium as it's moving around. Okay, let's just add one more piece, and what I'm going to do this time is I'm going to test the gas that comes off of the lithium. If I get a lit splint, and we're all very, very quiet. You may have heard a small pop. I'm going to react with water. It's going to be sodium. So again, I'm going to take a small piece of sodium out of the jar containing oil. And again, I'll hold it up once we've dried off some of this oil to show you that the surface is very dull. So again, I'm going to have to cut this. You might notice this did cut a lot easier than the lithium, so I have a shiny edge. I'm going to add a piece of sodium to this water, and again you can have a look and record what you see. Okay, again I'll add one more for you. Finally, the last of the group 1 metals that I'm going to be using today is potassium. Now, again, just removed a few pieces from the oil. I'm just going to dry them off. I'll show you again that the surface is quite dull, and when it's cut, we get those shiny edges that will cause a reaction. I'm going to add my piece of potassium into the water, and I'd like you again to record your observations. Okay, I'll just add one more piece. I'm just going to cut it so it's a little bit smaller because that was quite a big piece. Oh, go on, I'll do one more because both of those are quite quick and because it's my favourite one. Okay. Now, I did say at the start of the video that we were going to test the water before and afterwards. I'm just going to collect a little bit of water from after we had reacted to those metals with them. You should see when I add the universal indicator that the water before shows a green colour as it's pH 7, but the water after the reaction that's very purple, is alkali. And that is the reason that they call this group the alkali metals. Just to show you some of the elements I couldn't use in the video that I've just inserted, first of all, rubidium and then cesium. So as you can see from those two elements, the group 1 definitely increases in reactivity as you go down the group, because cesium has a significantly more violent reaction than lithium did. So the word equation for the reaction of lithium with water is lithium plus water forms lithium hydroxide plus hydrogen gas. Now that can also be represented as a symbol equation. So we could have, it's 2Li plus H2O forms 2LiOH plus H2. If I was to change the metal in this reaction, then if it's a group 1 metal, it will react in a similar way. So if it was sodium reacting with water, I would form sodium hydroxide and hydrogen. If it was potassium and water, I would form potassium hydroxide and hydrogen. Alkali metals also react with chlorine. The alkali metals will burst into flames when they are heated and then added to chlorine, and they will form metal chlorides. So I'm going to show you the reaction of sodium with chlorine. So as you can see here, quite a bright flame when you place heated sodium into chlorine gas, and the flame is yellow, and that is characteristic for sodium. So if you are asked what you would see a yellow flame. Now we're going to have a look at group 7, also known as the halogens. Now again, the halogens all react in similar ways, with water and with group 1 metals. They form diatomic molecules, which is why when we write chlorine gas, we put Cl2. And as you go down the group, the atomic radius increases because you've got more shells, the reactivity will decrease, and the melting and boiling point will increase. Now we can see this with the reaction of the halogens with hydrogen. Fluorine will react instantly with hydrogen, but as you go down the group, that reaction is less violent, so it will either need to be heated more or it will not react with hydrogen. A more reactive halogen will also displace a less reactive halogen from an aqueous solution of its salt. Now I have recorded this practical and I will insert it here. It's Mrs. Jennison here again. Today we're going to be doing a displacement reaction, and we're going to be doing displacement using the group 7 halogens and their halide salts. So for this experiment I need a spotting tile. I've got chlorine water, bromine water and iodine solution, and I've also got potassium chloride, potassium bromide and potassium iodide solution, and some teat pets. Also, in terms of safety, I'm going to wear my safety goggles throughout the experiment. I've got my lab coat on, I'm stood up, and I will be tying my hair back as well. And because some of these are quite dangerous, I'm in a very well ventilated room and I've got a fan to remove any fumes. So what I'm going to do is I'm going to set up my spotting tile so that I have columns of the salts and rows of the halogens. And what I will do is I will add a few drops of each salt solution into each of these dimples in the spotting tile, and then I will add a few drops of the halogen to see if there is a colour change If there is a colour change, that means a displacement reaction has taken place, which means the halogen, which has been added, is more reactive than the one that is in the compound, and they have swapped places. So, first I'm going to add a few drops of potassium chloride. Then I'm going to add a few drops of potassium bromide. Notice that I'm putting the lids on every bottle after I've used it because that's just good, safe lab practice. And then a few drops of potassium iodide. So now I've set those up, I'm going to add in a row a few drops of the chlorine water. And remember, I'm looking for a colour change. So, obviously chlorine is not going to react with itself, but I'm putting it in just so you can see. Okay, so I've just had a slight colour change there, which means chlorine must be more reactive than bromine. And again, I've had another colour change there. So that means chlorine is more reactive than iodine. So it's swapping places. It's displacing. Next, let's add the bromine water. Now, this is slightly pale yellow to begin with. So I'm just looking for it to change any more than its already pale yellow colour. Bromine won't react with itself, so we'll discount that one. And you can see we've got a slightly darker colour here, which means iodine is less reactive than bromine. Bromine's more reactive than iodine. And then I'm just going to add my iodine solution, which is very dark to begin with. So we're looking for it to get any darker than that, which that's not. They are all staying the same colour, which means iodine is the least reactive of the halogens because none of those were displaced. Chlorine is the most reactive of the halogens as it displaced bromine and it displaced iodine. So as we saw in the video, chlorine displaced the bromine from potassium bromide and displaced the iodide from potassium iodide. However, when bromine was placed in potassium chloride, there was no reaction because chlorine is more reactive than bromine. Now, you could be asked to complete displacement reaction word and symbol equations. So here, in this example, chlorine reacting with sodium bromide will form sodium chloride plus bromine. And another example, fluorine, when it reacts with sodium iodide, will produce sodium fluoride and iodine. Now, it's quite important here that you use the correct spelling and suffixes on the words when you are talking about the halogens. When the halogen atoms are atoms, their names end in "ene". So when you are talking about the element, it is fluorine, chlorine, bromine, and iodine. When these form their halide ions, the end of their name changes to be fluoride. So for example, sodium fluoride, sodium chloride, sodium bromide, and sodium iodide.